March 6, 1944, RAF Debden, England. Ground Crew Chief Master Sergeant Robert Hayes crouched beneath the left wing of P-51B serial number 436819, examining the silver cylindrical tank suspended from the pylon. The surface felt wrong under his palm. Textured, almost ribbed, nothing like the smooth aluminum of standard drop tanks. Paper. They're sending us into combat with fuel tanks made of paper. Hayes rapped his knuckles against the shell. The sound came back hollow, muffled, like striking a cardboard shipping drum. Hayes had serviced fighters since North Africa, had seen every improvisation desperation could conjure: patched wings held together with fabric and dope, engines rebuilt from scavenged parts, ammunition belts hand-loaded when supply chains broke down. But this crossed into absurdity. The tank's construction was visible even through the finish. 3 distinct sections bonded together, wrapped in what looked like layers of treated cardboard. Through gaps where the silver dope had chipped away, he could see the brown Kraft paper underneath, the same material used for grocery bags and shipping wrap. The seams between sections showed the laminated structure, dozens of paper layers glued together, building up thickness like plywood. Hayes traced his finger along one of the seams. The bond felt solid, but the entire concept violated everything he understood about fuel systems. Aviation gasoline was a solvent. It ate through rubber, dissolved paint, corroded metals, and they were trusting it to paper tanks held together with glue. The morning briefing had been explicit. These 108-gallon tanks would carry enough fuel to escort the bombers 600 miles into Germany, to Berlin, the first single-engine fighters to reach the German capital, but only if the paper held together at 25,000 feet, at speeds pushing 350 miles per hour through temperatures 40 degrees below zero, while high-octane fuel slowly attacked the adhesive bonds from inside. Hayes checked his watch. 0547 hours. The bombers were already forming up over the English countryside, 660 B-17s and B-24s climbing to altitude, their contrails sketching white lines across the dawn sky. In 13 minutes, 50 P-51s from the 4th Fighter Group would take off, each carrying 2 of these experimental tanks under their wings. The pilots had been briefed on the limitations. The resorcinol glue binding the paper layers would slowly dissolve from contact with aviation fuel. Maximum service life, 6 to 8 hours from the moment ground crews pumped in the first gallon. After that, the tanks would begin weeping fuel through the seams. By 10 hours, they'd be structurally compromised, useless for anything except emergency jettison. But 6 to 8 hours was enough. The mission profile called for tanks to be dropped over Germany once they were empty, long before degradation became critical. The fighters would be on internal fuel for the return journey. Simple, disposable, one-way logistics. The Luftwaffe's fighter tactics had evolved around a fundamental assumption. American Escort fighters had limited range. P-47 Thunderbolts, despite their ruggedness and firepower, could only escort to about 375 miles from base, even with external tanks. P-38 Lightnings pushed to 450 miles, but were vulnerable at high altitude where German fighters excelled. German interceptors had learned to wait, conserve their strength, let the escorts reach their fuel limits and turn back. Then they'd attack the bombers during the long, unprotected run over the target and the withdrawal. It had worked brutally well through 1943. October 14, 1943, Black Thursday, the 8th Air Force lost 60 bombers over Schweinfurt, 1/4 of the attacking force. The bomber offensive nearly collapsed under unsustainable casualties. Berlin had remained untouched precisely because it lay beyond escort range. The 1,100-mile round trip was impossible for any Allied fighter. The German capital was sanctuary, defended by the Luftwaffe's best units, secure in the knowledge that American bombers attempting to strike it would arrive alone and vulnerable. Until now. If these paper tanks worked, what happened next would defy all odds. If you're invested in this incredible story of innovation and courage, click the like button to support the channel and subscribe so you don't miss how this critical mission unfolded. Back to Hayes, the crews, and those fragile paper tanks. Hayes finished his inspection, signed off the maintenance log, and stepped back. Around him on the hard stand, 49 other crew chiefs were completing identical checks, the 334th, 335th, and 336th squadrons ready for the longest fighter mission of the war. Everything depended on paper and glue holding together for the outbound journey. The journey to this moment had begun 16 months earlier, not in American factories or engineering laboratories, but in the brick buildings and paper mills of southeastern England, where wartime necessity forced an impossible problem toward an unorthodox solution. November 1943, Bowater Lloyd's paper mill, Sittingbourne, Kent. The answer to the 8th Air Force's most critical problem was taking shape on wooden forms in a converted newsprint facility 50 miles east of London. Colonel Cass Huff of the U.S. Army Air Forces stood in the production hall watching workers wrap sheets of Kraft paper around cylindrical mandrels, each layer thoroughly saturated with resorcinol glue before the next was applied. Huff had spent the previous 8 months pursuing what the engineering staff at Wright Field in Dayton, Ohio dismissed as fantasy, a drop tank constructed from paper that could safely carry 108 gallons of high-octane aviation fuel without disintegrating. The challenge wasn't structural strength. Properly laminated Kraft paper could easily handle aerodynamic loads and internal fuel pressure. The problem was chemical compatibility. Aviation gasoline was specifically formulated to resist premature ignition in high-compression engines. That same chemical stability made it an aggressive solvent. It dissolved adhesives, degraded sealants, penetrated porous materials. Every glue Huff's team tested either failed immediately upon fuel contact or degraded within hours. Water-based adhesives dissolved. Oil-based adhesives were attacked chemically. Even synthetic resins showed poor resistance. The requirements were contradictory. The adhesive needed to create bonds strong enough to hold under 6 psi internal pressure while being flexible enough to survive thermal expansion and contraction from minus 40 degrees F at altitude to plus 80 degrees F on the ground, all while resisting chemical attack from one of the most aggressive solvents in common use. Resorcinol formaldehyde resin changed the equation. The phenolic adhesive created cross-linked polymer chains that bonded the paper's cellulose fibers into a composite matrix. More importantly, the cured resin showed remarkable resistance to petroleum distillates. Not immunity. Under sustained exposure, the fuel would eventually penetrate and weaken the bonds, but the degradation was slow, measured in hours rather than minutes. 6 to 8 hours of full fuel contact before the glue began failing. Not permanent, not reusable, but sufficient for a one-way trip into Germany and back. The manufacturing process was labor-intensive but required minimal skill. Workers cut Kraft paper, the same strong brown paper used for shopping bags and shipping wrap, into precisely sized sheets. For the nose and tail cone sections, the paper was cut into petal shapes, each piece overlapping the next like scales or roof shingles. This arrangement distributed stress and prevented crack propagation. For the cylindrical center section, continuous sheets were wrapped around the mandrel, building up layers incrementally. Each layer received a coating of resinol glue applied with spreading tools. The workers pressed the paper down with squeegees, working out air bubbles and wrinkles that would create weak spots in the final structure. Layer after layer, building thickness. The process took time. Rushing led to voids, delamination, structural failures. Before final assembly, wooden baffles were installed inside the tank body. These internal partitions prevented fuel from sloshing violently during flight maneuvers. An aircraft pulling 4 Gs in a hard turn subjects its fuel to tremendous forces. Fuel sloshing could shift the center of gravity enough to affect control. The baffles dampened these movements, keeping fuel distribution predictable. Metal components came next. A feed line with shutoff valve, a pressure equalization line to prevent vacuum formation as fuel drained, suspension lugs to attach the tank to the aircraft's pylon mounts. These fittings had to be bonded securely to paper. Metal inserts were embedded in the laminate structure during construction, creating mechanical interlocks reinforced by the surrounding paper layers.
The interior received multiple coats of fuel-resistant lacquer. This casein-based coating, made from milk protein, formed a barrier between the fuel and the glue, slowing chemical attack. It wasn't impermeable, but it bought time. The lacquer extended the tank's service life from 3 hours to 8, transforming a failed experiment into a marginally viable product. After the lacquer cured, the 3 sections, nose cone, center cylinder, tail cone, were bonded together in a press. More Resonol glue, more curing time. Then pressure testing. 6 psi of air pressure held for 10 minutes. Tanks that leaked failed inspection and were scrapped. Those that held pressure advanced to finishing. 2 coats of cellulose dope sealed the exterior, followed by 2 coats of aluminum paint. The silver finish served multiple purposes. It distinguished paper tanks from gray-painted metal tanks, reducing confusion during ground handling. It provided some thermal insulation, keeping fuel temperature more stable, and it made the tanks visible at a distance, important for pilots checking whether their external stores had released properly. Bowater Lloyd's had been producing Kraft paper products since the 1930s. Their mill processed wood pulp using the Kraft process, chemical treatment that preserved the long cellulose fibers, giving the paper its exceptional strength. The same paper used for reinforced envelopes and industrial packaging. Nothing exotic, just paper, glue, lacquer, and paint, assembled by semi-skilled workers who could be trained in days rather than months. Colonel Robert Schaefer, working alongside Huff, had championed the paper tank concept against considerable skepticism. When he presented the first prototypes to Wright Field, the Engineering Review Board issued a formal assessment. Paper tanks are absolutely unfeasible and will not do the job for which they are intended. The tanks leaked during testing, they said. The paper couldn't handle thermal stress. The concept was aeronautical folly. Schaefer and Huff ignored the assessment. By the time Wright Field's formal rejection arrived, operational squadrons in England were already using the tanks in combat. Engineering theory had collided with operational necessity, and necessity won. By December 1943, the Sittingbourne mill had established a production rhythm. Finished tanks emerged at a rate that would eventually total more than 13,000 units for RAF use, with similar numbers going to the 8th Air Force. Each tank weighed roughly 40 pounds empty compared to 150 pounds for an equivalent aluminum tank. Each required no aluminum, no steel beyond small fittings, no machine tooling, no skilled metal workers, just paper mill workers following procedures, building fuel tanks one layer at a time. The first operational test came on December 13, 1943. The 354th Fighter Group, newly equipped with P-51B Mustangs, flew Escort for bombers attacking U-boat construction facilities at Kiel. The target lay 490 miles from the group's base, beyond the range of any previous Escort mission. With paper drop tanks providing the fuel margin, the Mustangs not only reached Kiel, but engaged German fighters over the target, then escorted the bombers home. Pilots reported no issues. The tanks fed normally, released cleanly when dropped, caused no handling problems. The paper construction was invisible to the aircraft. It performed exactly like aluminum, just lighter and cheaper. 3 days later, the 354th flew another deep penetration mission, then another. The pattern was established. Paper tanks worked. The strategic bombing campaign, throttled by unsustainable losses through 1943, suddenly had the tool it needed, long-range fighter escort that could match the bombers anywhere they went. The mathematics of air warfare had fundamentally shifted. For 18 months, German defensive strategy had relied on range limitations strangling Allied offensive capability. That limitation was gone. January through February 1944, the pattern emerges across the theater. Through the winter of 1944, the paper tanks enabled operations that rewrote tactical thinking. P-51 groups ranged across Germany, their missions extending far beyond what P-47 Thunderbolts or P-38 Lightnings could achieve even with metal drop tanks. The P-47's range limit of 375 miles meant it could escort bombers only to the German border. The P-38's high-altitude performance problems made it vulnerable above 25,000 feet, where bombers operated and German interceptors lurked. The P-51, with paper tanks, could fly 700 miles. January through February 1944, the pattern emerges across the theater. Through the winter of 1944, the paper tanks enabled operations that rewrote tactical thinking. P-51 groups ranged across Germany, their missions extending far beyond what P-47 Thunderbolts or P-38 Lightnings could achieve even with metal drop tanks. The P-47's range limit of 375 miles meant it could escort bombers only to the German border. The P-38's high-altitude performance problems made it vulnerable above 25,000 feet, where bombers operated and German interceptors lurked. The P-51, with paper tanks, could fly 700 miles from base, fight at any altitude, and return. On January 11, 1944, the 354th Fighter Group escorted bombers to Ascherleben, deep in central Germany. Lieutenant Colonel James Howard, flying P-51B serial number 436315, became separated from his flight in heavy weather. When he emerged from the clouds, he found himself alone, watching German fighters positioning to attack the bomber formation. For more than 30 minutes, Howard single-handedly defended the bombers against repeated attacks by over 30 Messerschmitt Bf-109s and Focke-Wulf FW-190s. He made head-on passes, breaking up German attack formations. When his ammunition ran out, he continued making dry runs, forcing German pilots to break off their approaches. His actions, enabled by the fuel capacity the paper tanks provided to get him to Ascherleben in the first place, saved an entire bomber group from destruction. The Medal of Honor citation credited him with destroying at least 4 German aircraft and probably shooting down several more, but the real achievement was keeping the bombers alive. That mission exemplified what the paper tanks made possible: persistent fighter presence over targets deep in Germany. The Luftwaffe couldn't wait for escorts to reach their fuel limits and turn back. The escorts stayed. Through February, during the coordinated offensive Allied planners called Big Week, American and British bombers hit German aircraft production facilities in a sustained campaign intended to destroy the Luftwaffe's ability to build replacement fighters. The 8th Air Force flew nearly 3,800 bomber sorties, losing 226 aircraft, a loss rate of 6%, high but sustainable. In October 1943, before long-range escort, the loss rate was 9.1%, 60 bombers lost in a single day over Schweinfurt. The February mission struck Regensburg, Leipzig, Augsburg, Stuttgart, targets that would have been suicidal to attack without escort. The paper tanks enabled P-51s to be overhead when the bombers arrived, overhead during the bomb run, overhead during withdrawal. German interceptors had to fight through fighter screens to reach the bombers. Many never got through. But Berlin remained beyond reach. The German capital lay 550 miles from bases in England, 1,100 miles round trip. Even with paper tanks, the mission would push the P-51's range to its absolute limit. The fuel margin was razor thin. Adverse winds could make return impossible. Any combat maneuvering burned fuel at accelerated rates. Navigation errors could be fatal. Getting lost over Germany with minimum fuel meant dead pilots. The mission planner studied the numbers repeatedly. Internal fuel, 269 gallons. 2 108-gallon drop tanks, 216 gallons. Total, 485 gallons. Combat cruise consumption, 72 gallons per hour. Mission time, 6 hours minimum. Required fuel, 432 gallons. Margin, 53 gallons. 1 hour of reserve, assuming perfect navigation, no combat, favorable winds. It was barely possible, just barely, and it required the paper tanks to hold together for the entire outbound journey, 5 to 6 hours with fuel continuously attacking the glue that held the shells together. March 4, 1944, the first fighters over Berlin. At 600 hours on March 4, 1944, the 4th Fighter Group launched from RAF Debden. 50 P-51B Mustangs, each carrying two 108-gallon paper tanks under their wings, climbed through the morning darkness to their rendezvous altitude of 20,000 feet. Other groups joined from different bases, the 354th from Boxted, the 357th from Leiston. Altogether, 174 P-51s would escort the day's bomber stream to Berlin. Lieutenant Colonel Donald Blakesley, commanding the 4th Fighter Group, had personally briefed the mission. His instructions were explicit: maintain cruise settings until drop point, stay with the bombers, do not pursue German fighters away from the formation, do not waste fuel on individual combats. The mission was escort, not fighter sweep. Getting home alive mattered more than victories. The formation crossed the English coast at 6:55 hours, passing over Great Yarmouth at 21,000 feet. The North Sea stretched ahead, gray and cold under scattered clouds. The bombers were ahead and above, 660 B-17s and B-24s in combat box formations, stacked from 22,000 to 26,000 feet, their contrails marking the path into Germany. The P-51s maintained cruise power, 2050 RPM, 31 inches manifold pressure, mixture set to auto lean. At these settings, the Packard-built Rolls-Royce Merlin V1650-3 engine consumed roughly 70 gallons per hour, balancing fuel efficiency against the need to keep up with bombers cruising at 180 miles per hour indicated airspeed. The external tanks fed first, draining down as the formation pressed east across Holland. Below, the Dutch countryside appeared frozen, canals and fields locked in winter. The coastline fell away behind, German territory ahead. At 7:45 hours, near the German border, the fighters climbed to 24,000 feet to stay above the bombers. The external tanks were reading less than half full now, feeding steadily into the engine. The paper shells showed no signs of problems, no fuel leaks visible, no handling issues, no pressure problems. At 8:20 hours, approximately 300 miles from Berlin, the formation reached the calculated drop point. On command, 348 paper tanks tumbled away from the fighters, falling toward Germany 24,000 feet below. The fighters were now on internal fuel only, committed to the mission with no margin for error. The empty tanks fell for more than 3 minutes before hitting the ground, scattering across German territory. Some landed in fields, breaking apart on impact. Others fell through trees or into water. German civilians who found them sometimes mistook them for unexploded bombs until they got close enough to see the paper construction. Over Brunswick, at 0915 hours, the first German fighters appeared. Messerschmitt Bf-109s from Jagdgeschwader 3, climbing from airfields near Magdeburg. The German fighters probed the formation, looking for weaknesses, testing the escorts. The P-51s turned to meet them, and the Germans backed off, unwilling to commit against fighters that had altitude and position advantage. More contacts near Stendal. Then, as the formation approached Berlin, Luftwaffe fighters came up in strength. Jagdgeschwader 3, Jagdgeschwader 11, Jagdgeschwader 26, dozens of Bf-109s and FW-190s scrambled from fields surrounding the capital. Major Wilhelm Moritz, leading Jagdgeschwader 3, described the moment in his combat report. "We had expected bomber formations only. The presence of single-engine escort fighters over Berlin was considered impossible. When we identified Mustangs at our altitude, some pilots thought they were captured aircraft being flown by Germans. The realization that American fighters had reached Berlin changed our tactical situation completely." The battle over Berlin lasted 40 minutes. German fighters tried repeatedly to break through to the bombers. The P-51s stayed between them and the B-17s, turning into every attack, forcing the German pilots to either engage the escorts or break off. The Bf-109 G6, Germany's primary interceptor, could match the P-51 in level speed and climb below 20,000 feet, but above that altitude, the American fighter was superior in every performance category. The FW-190A8 had excellent low-altitude performance, but struggled in the thin air above 22,000 feet. Captain Don Gentile of the 336 Squadron, flying as Blakesley's wingman, engaged a Bf-109 that had gotten through the screen and was positioning for a head-on attack against the lead bomber box. Gentile rolled inverted, pulled through, came down behind the German fighter at high speed. A 2-second burst from his 4.50 caliber machine guns, 90 rounds total, ripped through the 109's fuselage. The German aircraft rolled right, trailing glycol smoke, and fell away into a dive. Gentile pulled back up to the bomber formation. Fuel state 165 gallons remaining, enough to get home if they started west immediately. The bombers released over Berlin through heavy flak at 10:45 hours, then turned for England. The P-51s formed up around them, heading west. The return journey tested fuel management skills. Pilots leaned their mixtures to the edge where the engine ran rough, trading power for endurance. They climbed to 28,000 feet where thinner air meant less drag. They calculated wind corrections constantly, adjusting heading to account for drift that would add distance to an already maxed-out range profile. By the time the formation crossed back over the Dutch coast at 13:15 hours, fuel gauges were reading minimums. Some pilots had less than 30 gallons remaining, 10 minutes of flight time at cruise settings. Blakesley radioed ahead for priority landing clearance. The first aircraft touched down at Debden at 13:42 hours, nearly 7 hours after takeoff. Several fighters landed with fuel gauges showing empty, running on reserve. In his after-action report, Blakesley wrote, "We have demonstrated that Berlin is within fighter escort range using current drop tank configurations. The enemy no longer possesses sanctuary anywhere in the Reich. The success of this mission validates operational use of paper construction external tanks. 0 failures attributable to tank construction occurred during the entire mission profile." 3 days later, on March 6th, the 4th Fighter Group returned to Berlin. This time they destroyed 20 German aircraft for the loss of 3 P-51s. 8 more missions to Berlin followed in March. The pattern was established. The Luftwaffe had to fight through fighter escort to reach the bombers, anywhere in Germany, at any time Allied planners chose to strike. The paper tanks had broken the Luftwaffe's defensive strategy, a defensive strategy that had been built on a single assumption: American fighters couldn't escort to Berlin. That assumption was now rubble. The design philosophy: building for exactly enough, not forever. The paper drop tank existed because strategic bombing had created a requirement that conventional manufacturing couldn't satisfy: extend single-engine fighter range by 600 miles without consuming strategic materials, without requiring complex manufacturing infrastructure, without depending on skilled labor, and deliver it in quantities sufficient to equip every fighter in the theater within months. Traditional aircraft fuel tanks represented the opposite of every one of those requirements. Metal tank construction demanded aluminum sheet stock, a strategic material, rationed across all aircraft production. It required hydraulic presses, welding equipment, or riveting machinery depending on construction method. It needed skilled metal workers who understood stress distribution, fuel system sealing, and structural design. Production time per unit ran to days or weeks depending on factory capacity and tooling setup. Britain in late 1943 had none of these resources available in the quantities required. Aluminum production was allocated to aircraft production. Machine shops were building guns, engines, and vehicle components. Skilled metal workers were distributed across hundreds of essential programs, all competing for the same labor pool. But Britain had paper mills, it had forests producing wood pulp, it had chemical companies manufacturing industrial adhesives for furniture, construction, and packaging industries. And it had a workforce that could be trained to laminate paper in a matter of days rather than the months required to train a skilled aircraft metal worker. The specification that emerged from the 8th Air Force's Materiel Command was brutally simple: contain 108 U.S. gallons of 100-octane aviation fuel for 6 to 8 hours without structural failure or excessive leakage beyond normal evaporation losses. Survive aerodynamic loads at speeds up to 350 miles per hour and altitudes up to 30,000 feet. function through temperature ranges from -40 degrees Fahrenheit at altitude to +80 degrees Fahrenheit on the ground. Cost a fraction of metal tank equivalent in both money and strategic resources. Be entirely disposable. No recovery, no reuse, no maintenance. Every single requirement pointed away from conventional construction methods. Traditional aluminum tanks were designed for durability because aircraft tanks needed to last for the aircraft's service life, potentially thousands of hours of flight time across dozens or hundreds of missions. That durability required heavy-gauge aluminum, complex sealing systems, corrosion-resistant coatings. All that engineering was optimization for reusability. But fighters dropped their external tanks on every combat mission. The tanks got one flight, then fell into enemy territory. Building them to last 100 missions was waste when they'd only fly once. The entire logic of durable construction was inverted. The design philosophy became optimize for the single use case, make it last exactly long enough, no longer. Paper and glue had precisely the properties this required. Paper was light, 1/4 the weight of aluminum for equivalent volume. Paper was strong enough when properly laminated. The cross-directional fiber orientation in Kraft paper created excellent strength-to-weight characteristics. Paper was cheap and abundant. Wood pulp was a renewable resource, and Britain's forests could sustain production indefinitely. The adhesive problem was where conventional thinking would have stopped the entire program. Aviation fuel dissolved most glues. Standard adhesives failed spectacularly when tested. Some lasted minutes, others hours. None survived the 6 to 8 hour requirement with any margin. This is where Colonel Huff's approach differed from traditional engineering. He didn't look for an adhesive that would last indefinitely. He looked for one that would last exactly long enough. The question wasn't what glue is fuel-proof, but rather what glue degrades slowly enough. Resorcinol formaldehyde resin fit the requirement. Under sustained fuel exposure, the bonds would eventually break down, but eventually meant 6 to 8 hours, exactly matching the mission profile. Tanks would be dropped long before degradation became critical. The fuel-resistant lacquer coating extended this slightly by creating a barrier layer, but the fundamental approach remained: build something that works for the duration required, not for eternity. This philosophy violated every principle of aircraft engineering that emphasized reliability, durability, redundancy. Aircraft components were designed with safety margins. Structures were tested to multiples of operational loads. Materials were selected for longevity. The entire engineering culture was built around making things that wouldn't fail. The paper tank was designed to fail, just not during the mission. After 8 hours, it would leak. After 10 hours, it might delaminate. After 20 hours, it would fall apart. None of that mattered because it would never see 20 hours. It would see 6 hours maximum, then drop away to be destroyed on impact. The production economics made the philosophy undeniable. An aluminum tank required approximately 50 to 75 pounds of aluminum sheet, several hours of skilled labor, access to metalworking machinery, and quality control inspection by trained personnel. Final cost was substantial. Some sources indicate $100 or more per unit in 1944 dollars when including all overhead. A paper tank required approximately 40 pounds of Kraft paper, resorcinol glue, lacquer, and paint. Labor was semi-skilled. Workers could be trained in days. No metalworking machinery required beyond basic cutting and assembly tools. Production time was days rather than weeks. The cost savings were dramatic, though exact figures remain unclear in available records. More importantly, paper tanks freed aluminum and skilled labor for aircraft production. Every 1,000 paper tanks produced was 30 to 40 tons of aluminum that could instead become aircraft structures. It was hundreds of man-hours of skilled metalworking labor that could build engines or airframes instead of disposable fuel tanks. The trade-off was obvious. Paper tanks couldn't be reused, couldn't be repaired, couldn't be refilled. They worked once, then were gone. But in the context of strategic bombing operations where tanks were dropped on every mission anyway, that wasn't a trade-off, it was optimization. The Luftwaffe would discover what production optimization meant when applied systematically across an entire air force. Through spring 1944, the 8th Air Force intensified deep penetration raids across Germany. Every major industrial center, every aircraft production facility, every synthetic oil refinery came within range of fighter-escorted bomber formations. The Luftwaffe's day fighter force, which had imposed unsustainable casualties on unescorted bomber raids throughout 1943, now faced combat mathematics that had fundamentally changed. The bomber loss rates quantified the transformation. In October 1943, before long-range fighter escort, the 8th Air Force's loss rate stood at 9.1% of sorties dispatched. On October 14, Black Thursday, 291 bombers attacked Schweinfurt. 60 failed to return. That level of attrition was unsustainable. At 9% losses, a bomber crew's statistical chance of completing a required 25-mission tour was effectively zero. By February 1944, with P-51s providing escort using paper tanks, loss rates dropped to 3.5%. By April 1944, for missions with complete fighter coverage, losses fell below 2%. Crew survival rates increased proportionally. A bomber crew now had reasonable statistical odds of completing their tour and going home. The Luftwaffe's fighter force experienced the inverse. German fighter pilot casualties, already severe from attrition on the Eastern Front, climbed sharply through spring 1944. Luftwaffe day fighter units faced American escorts not just at the extremes of range, but everywhere, continuously, for the entire duration of bomber missions. Major Heinz Baer, a Luftwaffe ace credited with 220 victories across all fronts, described the tactical transformation in his post-war interrogation. In 1943, we could select our moment of attack. We positioned above the bombers, waited for the American fighters to reach their fuel limit and turn back, then attacked at our chosen angle and speed. We controlled timing. By mid-1944, this was impossible. American fighters were over Germany from the moment bomber formations crossed the border until they departed. We had to fight through escorts to reach bombers, fight escorts while attacking bombers, fight escorts during our withdrawal. The external fuel capacity they carried meant they could remain over Germany for hours. Our pilots flew 3 or 4 missions daily and were exhausted. The Battle of Berlin, 16 major raids from March through April 1944, illustrated the shift in combat mathematics. Luftwaffe defenses shot down 625 Allied bombers during these missions, but German losses exceeded 1,000 fighters and, more critically, their pilots. Experienced Jagdgeschwader leaders who had survived years of combat on the eastern and western fronts were killed in action over their own capital. Oberstleutnant Egon Meyer, commander of GJ-2 and architect of head-on attack tactics against bomber formations, was killed March 2, 1944, by P-47 escorts before the Berlin missions even began. Major Hans Philipp, commander of GJ-1 with 206 victories, died October 8, 1943. Hauptmann Wilhelm Lemke, 131 victories, killed March 6, 1944, over Berlin. The replacement pilots arriving to fill these losses had minimal training. Luftwaffe fighter training programs, already compressed by fuel shortages and instructor losses, were producing pilots with as few as 20 flight hours in type before assignment to combat units. Some arrived at their squadrons never having fired their guns or practiced aerial combat. They faced P-51 pilots with hundreds of combat hours, superior aircraft performance at combat altitudes, and numerical superiority. On April 18, 1944, Major Thomas Hitchcock, who had championed the P-51 Mustang program and worked with the drop tank development team, died in a training accident in England. His P-51 entered an uncontrollable dive during a routine flight. The cause was never definitively established, though various theories about aircraft handling were investigated. Hitchcock's advocacy for the P-51 and extended-range operations had been instrumental in the program's success, but he didn't live to see the full impact of the capability he'd championed. By June 6, 1944, D-Day, Allied air superiority over Western Europe was absolute. German daylight operations had become effectively suicidal. Luftwaffe units conserved their remaining strength for night operations or transferred east to face the Soviet advance. The strategic bomber offensive continued through summer and fall with steadily increasing effectiveness, hitting oil production facilities, transportation networks, and industrial centers with precision that would have been impossible in 1943. The bombing of oil production proved particularly devastating. Luftwaffe flight training ceased for lack of aviation fuel. German panzer units were immobilized. The Wehrmacht's logistics network collapsed. Paper tanks had enabled the transformation. Without them, P-51s would have remained medium-range escorts, effective within 400 miles, but unable to reach deep into Germany. P-47s and P-38s couldn't fill the gap. They lacked either the range or the high-altitude performance, or both. Strategic bombing would have continued, but under the brutal loss rates that characterized 1943, when unescorted bombers were being destroyed faster than factories could replace them. Reichsmarschall Hermann Göring, commander of the Luftwaffe, reportedly understood the significance of fighters over Berlin. In post-war interrogation, he stated, "When I saw Mustangs over Berlin, I knew the jig was up." The instrument that made those Mustangs possible, the paper tank carrying fuel for the journey, had already been discarded. Dropped over German territory, the empty cylinders fell into fields and forests, breaking apart on impact. The Luftwaffe issued informational leaflets explaining to civilians that the strange cylindrical objects were harmless fuel tanks, not unexploded bombs. Production and deployment. Approximately 13,000 paper drop tanks produced for RAF use, 1943 to 1945. Approximately 15,000 additional units produced for USAAF 8th Air Force. Primary manufacturer, Bowder Lloyd's Paper Mill, Sittingbourne, Kent, England. Capacity, 108 U.S. gallons, 410 liters of high-octane aviation fuel. Empty weight, 40 pounds versus 150 pounds for equivalent aluminum construction. Service life, 6 to 8 hours from fueling before adhesive degradation caused leaks. Construction, laminated Kraft paper with resorcinol formaldehyde adhesive, casein lacquer coating, cellulose dope finish, aluminum paint. Strategic impact. First operational use, December 13, 1943, 354th Fighter Group Escort to Kiel, 490 miles. First Berlin Escort mission, March 4, 1944, 4th Fighter Group and others, 550 miles. Fighter escort radius extended from 400 miles, P-47 maximum, to 700-plus miles with P-51 and paper tank combination. Enabled complete bomber escort coverage to any target in Germany, eliminating Luftwaffe sanctuary areas. Combat effectiveness statistics. Bomber loss rate, 9.1% October 1943 pre-escort to 3.5% February 1944 to less than 2% April 1944, full escort coverage. Luftwaffe day fighter losses, over 1,000 aircraft March-April 1944 during Battle of Berlin. German synthetic fuel production, 175,000 tons April 1944 to 52,000 tons September 1944, due to sustained bombing enabled by extended escort range. Material and economic impact. Zero aluminum consumption per paper tank versus 50 to 75 pounds per metal equivalent. Estimated 500 to 1,000 tons of aluminum conserved for aircraft production. Production time, days for paper versus weeks for metal fabrication. Labor requirement, semi-skilled workers versus skilled aircraft metal workers. Cost savings, substantial, but exact figures remain undocumented in available records. Known survivors, approximately 4 to 6 complete examples surviving in museum collections worldwide: Smithsonian National Air and Space Museum, Washington, D.C., National Museum of the United States Air Force, Dayton, Ohio, Ulster Aviation Society, Long Kesh, Northern Ireland. Private collections, 2 to 3 examples known.
May 8, 1945. RAF Debden, England. Victory in Europe Day. Master Sergeant Robert Hayes stood on the flight line watching P-51Ds from the 4th Fighter Group taxi back from a victory flyover. The war in Europe was over. Germany had surrendered. The bombers and fighters were going home. The aircraft rolling past him carried metal drop tanks now, pressed aluminum, conventional construction. Production had caught up. Strategic materials were available. Manufacturing capacity exceeded demand. The crisis that had necessitated paper tanks was long past. Hayes had serviced fighters through the entire evolution. He'd watched the first paper tanks arrive in late 1943, had inspected hundreds of them, had never witnessed a single failure attributable to paper construction, not from structural collapse, not from fuel leakage severe enough to abort a mission, not from any of the catastrophic scenarios the engineering theorists at Wright Field had predicted. The tanks worked exactly as long as they needed to work. 6 hours, 8 hours, then they were dropped and forgotten. The principle established here would echo through logistics planning for the next 8 decades. When you need 10,000 of something immediately, building each unit to last forever is waste. Build them to last for the mission duration, using abundant materials, then move forward. Optimize for the actual requirement, not an idealized version of it. The paper tanks proved something that contradicted peacetime engineering logic. The optimal solution isn't always the most durable. Sometimes the optimal solution is deliberately temporary, designed to work exactly long enough and not 1 hour more. This thinking would define rapid deployment logistics through Korea, Vietnam, and beyond. Build what you need from what you have, deliver it when it matters, except that it won't last because it doesn't need to. The broader lesson went further. The Luftwaffe fell not to superior technology. German aircraft design in many categories exceeded Allied equivalents through 1944. The Luftwaffe fell to production optimization, to logistics thinking that valued quantity and availability over individual unit perfection. America and Britain didn't build the best fighter. They built good enough fighters in overwhelming numbers, supported by fuel systems that were good enough to enable the necessary missions. Paper and glue defeated the Luftwaffe. Not through combat capability. Paper tanks were never weapons. They defeated the Luftwaffe by solving the logistics problem that had protected German airspace for 3 years. They gave American fighters the range to escort bombers to Berlin, Munich, Regensburg, anywhere German industry operated. That capability destroyed the Luftwaffe's defensive strategy, forced German fighters into attrition they couldn't sustain, collapsed pilot training programs through fuel shortages, and ultimately eliminated German air resistance. The tanks that accomplished this transformation were design compromises in every category except the one that mattered. They worked when needed, where needed, in sufficient quantities to equip an entire air force. They cost almost nothing in strategic resources, required minimal skilled labor, and could be produced at rates that metal fabrication could never match. 3 paper tanks survive in the Smithsonian's collection. They sit in climate-controlled storage, the Kraft paper still intact, the laminated structure still holding together 8 decades after manufacture. The glue has long since lost its structural properties, but the paper remains, a testament to the durability of something designed to be temporary.